Hello, I am Professor Nagnath Hulle from GH Raisoni Institute of Engineering and Technology. In this video, we will try to understand the basics about the magnetic circuit. Basics about the magnetic circuit. I will explain first the basic definitions of the few terms, just like flux density, field strength, reluctance, and so on. I will start with the first definition. Here, the flux. Flux, it is defined as the creation of the line of magnetic forces in a magnetic material or in air. Is the definition of the flux, and its unit is Weber. This is basic definition you have learned at the 10 plus level. Now here I will start with the second definition, which is flux density. It is defined as the flux per unit area, and B is equal to phi by A, and its unit is Weber per meter square. A is the cross-sectional area of the magnetic path, and phi is the flux through the magnetic path. Next definition is MMF, that is magnetomotive force. It is defined as the force required to set up the flux or flux density in the magnetic material or in air. Its formula is MMF is equal to N into I, where N is the number of turns and I is the current flowing through that coil. Phi or other formula may be phi into S. This formula is very same as the formula of EMF, because we have the formula for EMF is equal to V is equal to I into R. This is similar to the I, and this is similar to the R, that is phi into S is the formula, and its unit is ampere turns. This MMF is very similar to the EMF in case of the electrical circuit. Means whatever we have the EMF in case of the electrical circuit, similar parameter in case of the magnetic circuit is the MMF. Now here the next definition is the permeability. It is the property of magnetic medium which allows to set up the flux or flux density in it. There are the two permeabilities. One is absolute permeability and relative permeability. And here absolute permeability is equal to mu naught into mu r, where mu naught is the permeability of the free space, which is 4 pi into 10 to the power of minus 7 henries per meter. This permeability is very similar to the conductivity in case of the electrical circuit. It is helping to set up the flux in the magnetic circuit. Then here next path or next definition is the reluctance. It is a property of magnetic material which opposes to the creation of the flux in it. Its formula is MMF divided by phi. This property is very similar to the resistance in case of the electrical circuit, because in case of the electrical circuit, resistance R is given by the expression V upon I. This is one formula, and other formula is in terms of the dimensions. Formula for the resistance is given by the equation. This R is equal to rho into L divided by A. The formula is rho into, this is L divided by A will be the formula. Rho into L divided by A. Now here in this case rho is replaced by 1 upon mu, otherwise everything is common. That's why for the reluctance we have the two formulas. One is MMF divided by phi, and other formula is in terms of its dimensions, that is L divided by A into mu, where mu is again mu naught into mu r, that is mu is absolute permeability, is the multiplication of relative permeability and the permeability of the free space. And its unit is, look at here, its unit is, that is ampere turn is the unit for MMF, and phi is the flux, its unit is Weber. That's why unit for the reluctance of the magnetic path is, it is ampere turn per Weber, and this is very similar to the resistance in case of the electrical circuit. Similarly here field strength, it is defined as the MMF per unit length of the magnetic path, and it is given by the expression H is equal to MMF upon L. MMF can be expressed as N into I divided by L, where Ni can be expressed as a phi into S divided by L. We will separate the phi and L here it is phi and L I have written here as it is. S is the reluctance, which can be written as something like this, which is L divided by A mu. Then in this case, this L will cancel with this value of the L. The remaining things is nothing but here phi divided by A mu, which is here. Readjusting the terms of this phi and A, means phi by A, this total divided by mu is nothing but this phi by A is nothing but the flux density, which is B, and mu is the permeability of that magnetic path. Means here its formula is ampere turn per meter. Is taken from basic definition. MMF is measured in terms of the ampere turns, and L is the length, which is measured in terms of the meter. That's why its unit is ampere turns per meter. Sometimes we can use this formula H is equal to B by mu, or we can use B is equal to mu H. That formula is also possible from its definition itself. Then here I have the second part here, that is comparison. Now here comparison of the electrical circuit and magnetic circuit we have considered. I have divided this particular topic into the two groups. One is the similarities of the electrical circuit and magnetic circuit, and the second topic is the differences between the electrical circuit and magnetic circuit. Now here I will start the discussion of the similarities of the electrical circuit and magnetic circuit. To start with, here this is the circuit diagram of, or this is the simple electrical circuit and this is the simple magnetic circuit. Here is the voltage in the circuit, which is known as EMF, and here is the MMF, the force which will create the flux or which will set up the flux, and here this EMF is electromotive force which produces the current I in the circuit. The opposition provided for the flow of current in the circuit is the resistance, and here the magnetic flux is a setup in the core, and the property of this core, which is opposing to creation of the flux in the magnetic path, is nothing but the reluctance, which is S. This reluctance is very same as the resistance in case of the electrical circuit. I have considered some points. I will go through the points here. It carries the current I, it carries the flux phi. Means current is very similar to the flux in case of the electrical circuit and magnetic circuit respectively. EMF is in case of the electrical circuit and MMF is in case of the magnetic circuit. Its formula is Ni, or which is phi into S is the other formula. Resistance is existing in case of the electrical circuit, which opposes to the flow of current, and reluctance is the magnetic circuit or magnetic path, which opposes to the creation of the flux in the magnetic circuit. In case of the electrical circuit, we have the resistivity. In case of the magnetic circuit, we have the reluctivity. In case of the electrical circuit, we have the conductance. In case of the magnetic circuit, we have the permeance. Similar parameter in case of the electrical circuit is the conductivity, and in case of the magnetic circuit, the similar parameter is known as the permeability of the magnetic path or magnetic medium. Now here, if we are going to the next topic, which is nothing but again comparison, but here we are going to understand or study the difference between the electrical circuit and the magnetic circuit. Here the first comparison point is some material acts as an insulator and does not allow the current flowing through it. Such materials are known as the insulator in case of the electrical circuit, just like that is plastic, wood. These are the insulators which will not allow the flow of current in those materials. But no such materials are exist for the magnetic path or magnetic circuit, because even the magnetic flux also passes through the air gap, because air is also not insulator for the flux. Second point for the discussion is the current flows through the conductor. Flux is not flowing through the conductor or not flowing through the magnetic circuit or magnetic path. It is set up or created in the magnetic circuit or in the magnetic path. When the conductor of resistance R carries the current I, it consumes the energy. Similarly, when a conductor of reluctance S carries the flux phi, it does not consume any energy in case of the magnetic circuit. Resistance calculation of the conductor is very accurate, but reluctance calculation of the magnetic circuit is appropriate value, because when we are using the formula for the calculation of the reluctance, that is L divided by A into mu naught. In that particular case, whatever the value of the reluctance we are getting, that is S, it is a high value in terms of 10 raised to the power of 6 and something. And if we are rounding those values in that particular case, the calculation will be the approximate calculation in place of the exact calculation. I give such examples while calculating the parameters based on the calculation of the magnetic circuit, that is calculation of the reluctance. Now here, if I am moving further, then while understanding the magnetic circuit, we must understand the 2 points, that is nothing but the leakage or leakage flux and fringing. These 2 concepts in case of the magnetic circuit. Now here, to understand the simple concept in case of the magnetic circuit, I have considered this figure, and in this figure consists of this magnetic core. This is the core, or this is a core of material or medium, and here is the winding. Here whatever the force available, that is known as MMF. Now here figure shows the magnetic circuit consisting of the iron core with air gap. Here whatever I have shown here, this is air gap. Means this actually this core completes here itself. This and whatever here we have, this gap is the air gap. Now here the flux in the air gap is utilized for some applications, and generally it is known as a useful flux. Generally it is known as a useful flux. Just I will take the example of the DC generator or a DC motor. In case of that, here we have the 2 magnets separated by some air gap, and here is a rotor, or here is the armature which is rotating in this particular case, and it will produce the electricity. Means here what I mean to say, the flux which is available inside the air gap is utilized for some purpose. That's why the flux available in the air gap is known as a useful flux, that is phi u. Similarly, what do you mean by the leakage flux? Now here practically it is found that flux is not confined to the magnetic path. Means all flux is not going through this path only, which is low reluctance path as far as the magnetic circuit is concerned. Some flux leakages through the air, maybe this direction, maybe this direction, or sometimes maybe in other directions also. And this flux which is not confined to the iron path and not available in the air gap for some applications, such flux is known as the useless flux, or sometimes it is known as a leakage flux, that is phi L. Means flux which is available in the air gap is the useful flux, and flux which does not confine to the iron path or to the core is known as the leakage flux, which is the phi u. Here I am coming to the last point, which is the fringing. Here fringing. What do you mean by the fringing? Spreading of the flux takes place at the edges of the air gap, due to which cross-sectional area of the air gap increases and flux density decreases. This effect is known as a fringing. Means how it is? Now here generally this is the end portion of the core, and between these 2 portions we have the air gap. This is air gap. What happens actually? The flux must go by this way. These are the line of the fluxes. But what happens at the edges of this air gap, the spreading of the flux takes place. And due to the spreading of the flux, here the area or cross-sectional area of the air gap increases. And due to the increase in the cross-sectional area, the flux density of the air gap decreases. And this particular effect is known as the fringing. Means in short, the spreading of the flux takes place at the edges of the air gap, which will increases the cross-sectional area, and due to which flux density decreases. This effect is nothing but the fringing effect. Now here I will give one definition here, and that definition is nothing but definition for the leakage factor, which is lambda. It is defined as the ratio of the total flux pi t to the useful flux phi u. Because in some cases here, sometimes while solving the problems, they will give the total flux, or sometimes they will give the useful flux, or sometimes they will give the leakage factor. By knowing one of the value, we have to calculate the other values. This lambda is equal to phi t upon phi u is the relation between the leakage factor and total flux and useful flux. That's it for as far as this magnetic circuit or basics of the magnetic circuits are concerned. And thank you for watching this video. In the next video, I will try to explain the problems based on the calculation as far as the magnetic circuits are concerned. That is nothing but basic magnetic circuit. Thank you.